Hello friends, here it is given that lambda mu nu be the roots of the equation x upon a plus k, y upon b plus k plus z upon c plus k is equal to 1 in k. Then prove that del xyz upon del lambda mu nu this is equal to minus times nu minus lambda, lambda minus mu, mu minus nu divided by a minus b, b minus c, c minus a. Here we have to find the Jacobian of x, y, z with respect to lambda mu nu. So you can see here the given equation is x upon a plus k, y upon b plus k, z upon c plus k. This is equal to 1. Now we solve this equation. So taking LCM and simplify this. So we get x times b plus k multiplied by c plus k, y times a plus k multiplied by c plus k, z times a plus k multiplied by b plus k is equal to a plus k multiplied by b plus k multiplied by c plus k. You can see here in the given equation, first we take LCM in the left hand side and then multiply in the right hand side. So we get this. Now this b plus k multiplied by c plus k, so we get here bc plus bk plus ck plus k square. Similarly here a plus k multiplied by c plus k, this is ac plus ak plus ck plus k square, plus z times here a plus k multiplied by b plus k, this is ab plus ak plus bk plus k square. Now in the right hand side, first we multiply a plus k by b plus k, so we get here ab plus ak plus bk plus k square and then multiply by c plus k. Now we simplify, we get x bc plus x bk plus x ck plus x k square plus y ac plus a k y plus c k y plus k square y plus z a b plus a k z plus b k z plus k square z plus a b c plus is equal to a b c plus a b k plus a c k plus a k square plus b c k plus b k square plus c k square plus k cube. You can see this is the simplification. Now this equation can be written as k cube here. You can see this is k cube. Now we taking k square term, this is bk square, ak square. So taking common a k square here. So a plus b plus c, and from the left hand side you can see here this is xk square, yk square and zk square. So this is minus x minus y minus z. Now we write k. So in the left hand side, in the right hand side we can see here this is abk, ack and bck. So we write here ab plus bc plus ca. In the left hand side you can see here this is minus bx minus cx minus here ay minus cy and minus az minus bz and plus here constant term we write abc. Here you can see this is abc, and from the left hand side we can write xbc yac zab here. So you can see that this is the equation in k cube. This is the cubic equation in k. So this has three roots, and the three roots are given here, lambda, mu and nu. So first we find here sum of the roots lambda plus mu plus nu. This is here minus times a plus b plus c minus x minus y minus z divided by 1. This is the sum of roots of the cubic equation. So this can be written as lambda plus mu plus nu is equal to x plus y plus z minus a minus b minus c. Suppose that this is 1. Now similarly we find the sum of the product of two roots, that means lambda mu plus mu nu plus nu lambda. This is equal to a2 upon a naught. So this can be written as ab plus bc plus ca minus bx minus cx minus ay minus cy minus az minus bz. Suppose this is second, and we find the product of all three roots lambda, mu and nu. This is equal to minus times abc xdx xbc minus yac minus zab. So this becomes xbc plus yac plus zab minus abc. Suppose that this is third. We write here formula. If you can see here, if ax cube plus bx square plus cx plus d is equal to 0, this is the cubic equation. If alpha, beta, gamma be the roots of this cubic equation, then we can find alpha plus beta plus gamma by formula minus b upon a. Alpha beta plus beta gamma plus gamma alpha is equal to a2. A is equal to c upon a, and alpha beta gamma can be written as minus d upon a. You can write here, this is the formula for finding the sum of the roots in cubic equation and sum of the product of two roots in cubic equation and product of the three roots in cubic equation. Here you can see that this 1, 2 and 3, these are the implicit relation between the roots of the given equation in K and the variables x, y, z. So we write here. Now we write here the implicit relation in the form f1, this is equal to lambda plus mu plus nu plus minus x minus y minus z plus a plus b plus c. The second relation f2 can be written as lambda mu plus mu nu plus nu lambda minus ab minus bc minus ca plus bx plus cx plus ay plus cy plus az plus bz. Similarly, third implicit relation is given by lambda mu nu minus bcx minus acy minus abz plus abc. Here we can see the implicit relation is given. So first we find Jacobian of f1, f2, f3 with respect to x, y, z. So we find here Jacobian of f1, f2, f3 with respect to x, y, z. So by the definition this can be written as del f1 by del x, del f1 by del y, del f1 by del z, del f2 by del x, del f2 by del y, del f2 by del z, del f3 by del x, del f3 by del y, del f3 by del z. So here del f1 by del x. So del f1 by del x can be written as del f1 by del x can be written as minus 1. Here we differentiate partially f1 with respect to x, we get minus 1. f1 with respect to y, we get also minus 1. And when we differentiate partially f1 with respect to z, we get minus 1. Now we differentiate f2 partially with respect to x, y and z. So we get b plus c, c plus a and a plus b. Similarly, we differentiate partially f3 with respect to x, y, z. So when we differentiate with respect to x, we get minus bc, with respect to y minus ac, and with respect to z minus ab. Now we solve this determinant and find the value of this third order determinant. Now we find the value of the third order determinant. So del f1, f2, f3 divided by del x, y, z can be written as, here we solve this third order determinant. So for solving this, first here c2 tending to c2 minus c1 and c3 tending to c3 minus c1. We apply these operations, c2 tending to c2 minus c1 and c3 tending to c3 minus c1. So we get here minus 1 b plus c minus bc, and minus 1 subtract by minus 1, we get 0 here. C plus a minus b minus c, we get here a minus b, minus ac plus bc. So taking common c here, so this is b minus a. Similarly, when we subtract c1 column from c3, we get here 0, and a plus b minus c, b is cancelled out, so there will be a minus c, and minus ab subtract minus bc, we get b is common and c minus a. Now you can see here we taking common minus from the second row, so this becomes minus 1 0 0 b plus c, and taking common minus 1, so this is b minus a, and taking common here this is a minus b, taking common here minus, so this is c minus a, here minus bc, and taking common here, so this is a minus b, here c minus a. Now we taking common a minus b from second column and c minus a from third column. So this becomes a minus b, c minus a, and minus 1 b plus c minus bc 0 1 minus c 0 minus 1 and b. Now again we apply operation. Here c3 adding with c2. So a minus b, c minus a, and minus 1 b plus c minus bc 0 1 minus c 0 0 b minus c. Here we apply the operation c3 tending to c3 plus c2. You can see that this is lower triangular, this is the determinant of lower triangular matrix. So value of this determinant is the product of the elements of leading diagonal. So this is equal to a minus b, c minus a, minus 1 1 multiplied by b minus c. So this is minus times a minus b, b minus c, c minus a. So this is the Jacobian of f1, f2, f3 with respect to x, y, z. Now we find Jacobian of f1, f2, f3 with respect to the variables lambda, mu, nu. Now we find the Jacobian of f1, f2, f3 with respect to lambda, mu, nu. So this will be del f1, f2, f3 divided by del lambda, mu, nu. This is equal to del f1 upon del lambda, del f1 upon del mu, del f1 upon del nu, del f2 upon del lambda, del f2 upon del mu, del f2 upon del nu, del f3 upon del lambda, del f3 upon del mu, del f3 upon del nu. This is by the definition of the Jacobian we can write. Now we put values of the partial derivatives. First we differentiate f1 partially with respect to lambda, we get 1. With respect to mu, we get also 1. With respect to nu, we get also 1. Now, we differentiate partially with respect to lambda, f2. So, there will be mu plus nu. Now, we differentiate f2 partially with respect to mu. So, we get lambda plus nu. When we differentiate partially f2 with respect to nu, we get mu plus lambda. Similarly, we differentiate f3 partially with respect to lambda, we get mu nu. With respect to mu, we get lambda nu, and we differentiate f3 partially with respect to nu, we get lambda mu. Now we solve this third order determinant. Now we solve the third order determinant and find the Jacobian of f1, f2, f3 with respect to lambda, mu and nu. This is equal to, here we apply some operations of matrices of determinant. So C2 tending to C2 minus C1 and C3 tending to C3 minus C1. So we get here 1 mu plus nu and mu nu. Here we write 0 and nu plus lambda minus mu minus nu. So nu is cancelled out. Here we get lambda minus mu. Similarly, there will be nu is common, lambda minus mu, and when we subtract C3 minus C1 we get 0 here, and mu plus lambda minus mu, so there will be lambda minus mu, and here lambda mu minus mu, so mu is common here and we get lambda minus mu. So this is the third order determinant. Now you can see here lambda minus mu is common from second column and lambda minus mu common from third column. So there will be lambda minus mu, and 1 mu plus mu, 0, 1 mu and 0, 1 mu. Now again we apply the operation in the determinant. So we get lambda minus mu, and 1 mu plus mu, and 0, 1 mu and 0, 0 and mu minus mu. Now we solve this third order determinant. You can see that this is the determinant of lower trigonometrics. So value of this determinant is the product of the elements of leading diagonal. So there will be lambda minus mu, 1, 1 and mu minus mu. So this will be lambda minus mu minus nu, and we take common here minus 1 from lambda minus mu, we get here minus, and here nu minus lambda. So this is the Jacobian of f1, f2, f3 with respect to lambda mu nu. Now we have to find here Jacobian of x, y, z with respect to lambda mu nu. So we using here formula minus 1 to the power 3. Here 3 is the number of variables. There are 3 variables, lambda, mu and nu. So we use here in the power 3. Now in the numerator we write here Jacobian of f1, f2, f3 with respect to lambda mu nu divided by Jacobian of f1, f2, f3 with respect to x, y, z in the denominator. This formula is used when the implicit relation is given. Here minus 1 whole cube, this is minus 1, and here you know that Jacobian of f1, f2, f3 with respect to lambda mu nu is minus times lambda minus mu, mu minus nu and nu minus lambda, and Jacobian of f1, f2, f3 with respect to x, y, z can be written as minus times a minus b, b minus c, c minus a. Now you can see that this minus and minus plus here, and this is minus. So this Jacobian of x, y, z with respect to lambda, mu and nu, this is equal to minus times lambda minus mu, mu minus nu, nu minus lambda divided by a minus b, b minus c and c minus a. Thank you.